Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Fermi-Dirac statistics. Let's begin. To derive Fermi-Dirac statistics, we have to consider an isolated thermodynamic system, and that isolated thermodynamic system consisting of n number of identical with indistinguishable particles, and these particles obey Fermi-Dirac statistics. These particles are called fermions. Some basic properties of fermions we know that the particles having spin is intrinsic angular momentum the fermions having spin is odd integral multiple, means it is either half, 3/2, 5/2 like this, and these particles obey Pauli exclusion principle. What is Pauli exclusion principle? No two particles may occupy the same state at the same time, means in a single energy level we have only one identical particles or no two or more particles within that of single energy level. That is the Pauli exclusion principle, and the fermions obey that particular principle. Some examples of fermions: electrons, protons, neutrons, neutrinos, muons. These particles are under fermions. To derive the statistics, means how energy is distributed among fermions, we consider a system, and that system is divided into k number of compartments. Let n1, n2, ni up to nk are the number of particles having mean energy u1, u2, ui up to uk respectively, corresponding to the compartments. These compartments numbered as 1, 2, I up to k, and each compartment further divided into a large number of elementary cells G1, G2, Gi up to Gk. In that of thermodynamic system where fermions are there, let that system we divide k number of compartments. Compartment number 1, 2, 3, 4 up to I and k. In compartment number 1, the number of particles at n1, here n2, n3, n4, ni, nk. That compartments are further divided into large number of elementary cells. These are G1, G2, G3, G4, Gi and Gk, and these particles having mean energies u1, u2, u3, u4, ui to uk. To calculate that statistics, let we prefer that ith compartment. This is the ith compartment. Let you choose the ith compartment. For ith compartment, it has ni number of particles having mean energy ui and the number of elemental cells as ci. As we say, fermions satisfy Pauli exclusion principle. Since fermions satisfy Pauli exclusion principle, so no two same particles are in a same energy level, so we can say the number of elementary cells Gi that ith compartment is divided is greater than the number of particles Ni within that of cell, and these particles are identical with indistinguishable, means there is no such distinction between these particles, and these particles are arranged in various ways in which ni number of particles are chosen at a time. Therefore, we can say the number of different ways of arranging Ni fermions among Gi cells. What be the number of different ways we can arrange Ni number of fermions among Gi number of cells? That can be obtained using a mathematical tool, that is combination. So Gi combination Ni, that will be the number of different ways of arranging Ni number of fermions among Gi number of cells, that is Gi combination Ni. Therefore, the thermodynamic probability of that of system easily calculated. The thermodynamic probability of the system is given by the thermodynamic probability is the most number of macrostate, that is W is equal to, in the product multiplier I from 1 to k, as ith compartment the number of different arrangement Gi combination Ni. Similarly, for 1th compartment it is G1 combination N1, like this. So we use multipliers Gi combination Ni, or W is equal to that product from I from 1 to k, that combination as Gi factorial divided by ni factorial into gi minus ni factorial. Taking logarithm on both sides, ln w is equal to, that product change to summation, so it's summation over I log of a by b, that is log a minus log b. So log ln gi factorial minus ln ni factorial into gi minus ni factorial. Again log ab, that is log a plus log b, ln w is equal to summation over I ln gi factorial minus ln a ln b, so ln ni factorial plus ln gi minus ni factorial. Or ln w is equal to summation over I ln gi factorial minus ln ni factorial minus ln gi minus ni factorial. Next, log of any factorial can be evaluated by using Stirling's approximation, Stirling's formula. Using Stirling's formula as ln n factorial is equal to n ln n minus n. Therefore, ln w is equal to summation over I ln gi factorial gi ln gi minus gi minus ln ni factorial ni ln ni minus ni minus ln gi minus ni factorial gi minus ni ln gi minus ni minus gi minus ni. Okay. Next, evaluating that bracket terms summation over I gi ln gi minus gi minus ni ln ni minus minus plus ni. Next, minus gi minus ni whole into ln gi minus ni, here minus gi plus ni. Here the term minus plus is plus gni, minus plus minus ni. Okay, plus gi minus gi plus ni minus ni cancelled out. The term we obtain, that is summation over I gi ln gi minus Ni ln Ni minus Gi minus Ni whole into ln Gi minus Ni. That for ln W ln W. To find the state of maximum thermodynamic probability, that for equilibrium state, first we have to differentiate both sides, and keeping in mind that Ni is variable and Gi as constant, differentiating both sides, taking Ni as vary but Gi as constant. Okay, differentiation as d of ln W is equal to summation over I Gi ln Gi, entire constant, it will be 0. Next, minus Ni ln Ni, first term differentiation, second term as constant, second term differentiation, first term as constant, so it will be minus Ni into 1 by Ni dni minus dni into ln Ni. Next term, here minus Gi minus Ni as constant, differentiation of that term as 1 divided by Gi minus Ni, again differentiating, minus dni. Okay, next plus dni, minus minus plus, so it is dni constant ln Gi minus Ni, differentiation of that term, this term as constant. Solve that bracket, Ni cancelled out, Gi minus Ni cancelled out, so we obtain d of ln W is equal to summation over I ln Gi minus Ni. First write all the terms, minus dni minus dni ln Ni minus minus plus dni plus dni into ln Gi minus Ni plus dni minus dni cancelled out. In these two terms we take dni as common, or d of ln W is equal to summation over I ln Gi minus Ni minus ln Ni common dni. Okay, for a system to be in equilibrium, the thermodynamic probability will be maximum. Thermodynamic probability W will be maximum. Therefore, D ln W are 0. For maxima, its first order differentiation is 0. Therefore, that summation term, summation over I ln Gi minus Ni minus ln Ni whole into dNi is equal to 0. That equation number 1. As we consider an isolated system, so it is satisfy two constraints. One is total number of particles in that of system is constant, and total number of energy within that of system is constant. As it is an isolated system, so the total number of particles within this is a constant, that is total number of particles n, which is the summation over I from 1 to k Ni is a constant. Therefore, its differentiation as dn is equal to summation over I from 1 to k dni is equal to 0. So, that expression is written as summation over I from 1 to k dni is equal to 0. That equation number 2. Similarly, as we say, in an isolated system, the total energy will be constant. Second aspect, second constraint. Similarly, total energy within that isolated system is constant, that is total energy U is equal to summation over I from 1 to k Ni into Ui, number of particles, and its mean energy, which is constant. Therefore, its differential du is equal to summation over I from 1 to k, which is dni into ui is equal to 0. Therefore, we write summation over I from 1 to k ui into dni is equal to 0. That is equation number 3. Now, we can multiply a constant alpha by equation number 2 and another constant beta to equation number 3 and subtract from that of equation number 1. Multiply alpha in equation number 2, beta in equation 3, and subtract from equation number 1 we get equation number 1 summation over I ln gi minus ni minus ln ni. Next alpha is multiplied here, so it will be alpha minus alpha, beta is multiplied there, minus beta into ui. In that of expression dni as common is equal to 0. As we said, dni is independent. Various terms for different values of I are independent of each other. So within that of bracket term will be 0. Therefore ln gi minus ni minus ln ni minus alpha minus beta ui is equal to 0, as dni is independent, as for different values of I are independent each other, Therefore dni is independent, and that entire bracket term will be 0. Ln a minus ln b, that is ln a by b, gi minus ni divided by ni is equal to alpha plus beta ui, or its logarithm term in this side as exponential. So gi minus ni divided by ni is equal to e to the power alpha plus beta ui. Now it is gi divided by ni minus 1 is equal to e to the power alpha plus beta ui, or gi minus ni, that 1 is added, so it will be e to the power alpha plus beta ui plus 1. Our requirement is to calculate ni, so the expression for ni is equal to gi divided by e to the power alpha plus beta ui plus 1. If we put the value of beta, which is constant, as 1 by kt, so that expression now changes to ni is equal to gi divided by e to the power a plus b, e to the power a into e to the power b, so e to the power alpha into e to the power beta as kt, so ui divided by kt plus 1, that will be the required expression, which is called Fermi-Dirac distribution law. This is called Fermi-Dirac distribution law for energy. So here, with the help of this video lecture, we understand the concept of Fermi-Dirac statistics. We consider an isolated system having identical indistinguishable particles, and these particles obey Fermi-Dirac statistics, means these are fermions, and we know fermions are obey Pauli exclusion principle. So the number of elementary cells is greater than that of number of particles within that of compartments. By using that concept, the thermodynamic probability of that of system is calculated. mathematically we proceed, and finally for most probable macro state, that is in equilibrium state, so its differential will be 0. Another two constraints, number of particles in an isolated system is constant, total amount of energy again constant within that of isolated system. Two constants are multiplied to equation number 2 and 3, alpha in equation number 2, beta in equation number 3, and subtracted from that of equation number 1, and finally we obtain the expression for Fermi-Dirac distribution law. So with this useful and informative notes, let me wind up the session. Thank you.